NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, ladies and gentlemen. How is it? Oh, thank you. How is everyone tonight? Good. Well, again, thank you all so much for coming out to join us. What will the first evidence of life outside our own solar system look like? And what future technologies are required to discover that evidence? The challenge is that exoplanet-hunting space-borne telescopes must suppress the bright glare from stars up to 10 billion times in order to directly image the faint reflected light from a planet and look for telltale signatures of life. To tackle this, the Jet Propulsion Laboratory is developing two novel starlight suppression approaches, coronagraphs and starshades. Tonight we'll discuss what these technologies are, where they are today, and how they must evolve in order to support possible exoplanet missions in the next decade and beyond. Tonight's guest is an astrophysicist and the chief technologist for NASA's exoplanet exploration program located here at JPL. With his team, he helps identify and mature technologies needed for possible future NASA missions that will ultimately look for evidence of life on exoplanets. He received his PhD and master's from the University of Arizona, an MBA from the Rotterdam School of Management in the Netherlands, and a bachelor's in chemical engineering from the Stevens Institute of Technology in New Jersey, and has worked at the Jet Propulsion Laboratory in a variety of systems engineering and project management roles for the last 8 years. He's also a fine example of how it's never too late to chase your dreams. At the age of 33, he left an international career in chemical manufacturing while working for a subsidiary of a large consumer goods company, and went back to school to become an astrophysicist, his boyhood dream. The journey took him 9.5 years from restarting as an undergraduate at Harvard University, concentrating in physics, to finally completing his PhD in 2007. Needless to say, we're happy he stuck with it. Ladies and gentlemen, please help me welcome tonight's guest, Dr. Nick Siegler.
All right. Good evening, everyone. For countless generations, over many millennia, people have wondered, are there other worlds like ours elsewhere? Not necessarily blue, but alive. We are very privileged to be amongst the first generations to actually be on the verge of answering that age-old question, are we alone? So tonight we're going to go on a short cosmic journey together. We're going to bring you up to date on what we've learned about planets orbiting other stars. We're going to tell you a little bit about the techniques of discovering life on those planets, the technologies that enable that discovery, and finally we'll tell you a little bit about the missions that NASA is considering. So please bring your chairs to an upright position, stow away your tables, fasten your seatbelts. Let's begin. So this blue smudge that you could perhaps barely see in the middle of the screen is the largest stellar cluster in our galaxy. It's called the Omega Centauri cluster. It has 10 million stars in it. Now, 10 million is a lot of stars, but it doesn't feel like a large number until you see the heart of this cluster through the eyes of the Hubble Space Telescope. I have seen this picture hundreds of times since I was a young man, and I continue to be stirred by it. Look at the concentration, the density, the different sizes and colors of all of these stars in such a small distance. How could there not be at least one star harboring one planet, harboring or rooting the beginnings of life on at least one of the planets? At least one. It almost seems statistically impossible that there is not life on at least one of these planets. If we take this mass of stars and place it in or nearby the halo of our largest nearby galactic neighbor, this is the Andromeda Galaxy, it would only take up a small little dot in that entire galaxy. In our own galaxy, there are hundreds of billions of stars. And there is evidence to back up the fact that there are as many galaxies in the universe as there are stars in our own galaxy. So that's hundreds of billions of galaxies. This is what a lot of galaxies look like. This is a picture from the Hubble Space Telescope with its shutter open for 23 days. Every smudge on this image, other than a few foreground stars, are galaxies, each containing tens of billions of stars. If we are the only creatures to be alive in our galaxy, you can't help but ask, why all this space? Why all these galaxies? Why all these stars? Why all these planets? Alas, here we are meeting together in the first half of the 21st century, and there is no evidence to the contrary. We have no evidence for life outside of our own planet. However, it's still early days. I kind of think of it akin to some of the earliest hominids who marching out to the edge of their own lands, looking out over the sea, wondering, are there other lands near the horizon? Are there other sentient beings? And we now know that indeed there are other worlds across the sea of space, and we call them exoplanets. Exo means, in Greek, outside of our own solar system. So it just so happens that 20 years ago this year, the first exoplanet was discovered around this star 51 Pegasi. The two Swiss astronomers who discovered the planet never actually saw it because the star is just too bright. So they used a technique called radial velocity. And the way the technique works is if you can't see the planet, you can look at the star. And the way it works is the planet adds a gravitational tug to the star. So if you look at the star, it's wobbling, and that's due to the presence of the planet. So even though you don't see the planet, you know it's there. In fact, here's some of the early data that confirms the oscillatory nature of the wobbling. What's absolutely amazing about this discovery is that the planet, about the size of our own Jupiter, only required 4.2 days to make one trip around its star. 4.2 days, a far cry from our own Jupiter, which takes 11 years. So this was a harbinger of things to come, that exoplanets are very diverse and very surprising. We had no idea this was going to happen. In fact, there's evidence to suggest that the planet orbiting this star is evaporating. It's being vaporized by its own star. So let's fast forward 20 years. And here's where we are today. I checked our own database, 1,838 confirmed exoplanets. And believe me, these are the ones we've confirmed. We know that there are certainly many, many more. And as you can see, I show the planet discoveries by year, and it's clearly increasing. I've color-coded them, so we see that the blues correspond to the technique in which they were discovered. So blue is radial velocity, and we just discussed that. And you can see around 2010 or so, the blue starts to transition to green as being the more dominant technique. What is the green? It's a technique called transiting. So transiting has been championed by a NASA telescope called Kepler. And it is a very, very simple technique. Kepler stares at about 150,000 stars in our galaxy, all at the same time, just hoping, that there would be a planet that just serendipitously travels across the face such that the brightness of that star dips a little bit. And then when the planet reaches the other side, the brightness of the star will resume to where it was. Very simple. And that infers the presence of a planet, especially when the astronomers notice that it repeats itself, which indicates that the planet is traveling around that star. Astronomers then take that information of the period, they plug it into, ironically, Johannes Kepler's third law of orbital motion, and they can extract the separations, the distance between the planet and the star. And that becomes very important because it tells us a little bit about habitability, the distance. So Kepler, and this is an artist illustration, Kepler has only looked at a sliver of the overall stars in our galaxy. In fact, the radial velocity technique and others only comprise a small area, even smaller than what Kepler has looked at. However, even from this small sample, we have accumulated enough evidence to conclude a couple things. First is the diversity of planets and the commonness of planets. Let's take a look at the diversity of planets. The next 7 or 8 slides are all going to be artists' illustrations. These are not photos. We don't actually know what these planets look like. But speaking of diversity, there's evidence to suggest that there are planets, this one in the foreground, that are rocky and very close to the star, very similar to what we saw about 51 Pegasi. But because it's rocky, there's evidence to suggest that this planet remains in a molten state permanently, not very conducive to life. There's evidence for ice planets. We don't have ice planets in our own solar system. We have icy moons, but no icy planets. These are rocky planets that are sufficiently far away from their stars where the evidence suggests that any carbon dioxide or water has crystallized to ice. Again, not conducive for life, at least as we know it. Now, planets orbiting 2 stars, that's something that we had hoped would be true. Why? Because most stars in the evening sky actually are in multiple systems. So it was very important to us to know, can planets survive having multiple stars? And sure enough, Kepler has discovered evidence for this. In fact, this is an interesting case where reality imitates fiction. Some of you may be familiar with the Star Wars planet Tatooine, where they show 2 stars. Folks, it is real. Here's a planet that has been weighed in at 10 times the mass of our largest planet, Jupiter. 10 times its mass. What's equally as fascinating is this star is orbiting a star that happens to be in a quadruple system. We never thought that was possible. It speaks to the robustness of planets, that they can survive the somewhat unstable dynamics of stellar motion. In some cases, we've acquired the mass and the volume of the planet. And if for those of you that remember your physics, mass divided by volume gives you density. The inference is that some of these planets are made up large amounts of water. The density is consistent with that. May not be, but we believe that there are planets out there that have 40 to 50%, maybe even more, by mass water. And our planet is, even though it looks watery to you, is less than 1% water by mass. All planetary systems. So we found stars that have multiple planets orbiting it, which is what we would have expected. Similar to our own solar system, where we have 8 planets, there is substantial evidence that a lot of the stars have multiple planets. In fact, at least 40% of all the stars we've discovered so far are in multiple systems. What's fascinating about this particular star, it's Kepler 444, is its age. So scientists have concluded that the age of this star is around 11 billion years old. And that's important for a couple of reasons. One, it speaks to the quickness in which planets formed. We didn't know how long it would take. Second, which might be interesting to us, is it tells you how much time alien life could have had. 11 billion years is a long time. I wonder how sophisticated and advanced alien life may have become. Here's something we never would have guessed. There are evidence for nomadic planets, planets floating through the galaxy unbounded to any star. We never predicted that. And the evidence for this is through a technique called gravitational microlensing. It's another indirect technique. And then lastly, here's Neptune, roughly 4 times the size of our own Earth. And in our own solar system, there are no other planets that bridge this distance, this separation in size. So there's no reason why we can't find planets of an intermediate size. We just never have. Well, sure enough, Kepler has found a whole range of planets in between these two distances, and we call them super-Earths. We have no idea if these super-Earths are just larger versions of our own Earth. They could be maybe smaller versions of the ice giant Neptune, or maybe they're these water worlds. Still very exciting to figure out what they are. So I think you'll agree that there's enormous diversity in exoplanets that we did not actually predict, and a lot of them are nowhere similar to what we have in our own solar system. So let me show you what I believe are some of the 3 profound results from Kepler. And I have 3 of them. First one, planets orbiting other stars in the galaxy are indeed common. So when you look up at the night sky, on average, every single one of those stars has at least one planet around it, and maybe a whole planetary system. That's something we did not know even a few years ago. To add a little more data, it's actually the stars that you don't see that are equally as interesting. There's a whole population of very dim stars. Some of you may have heard of them. They're called M dwarfs or M stars. These very faint stars, about half the luminosity of our own sun, if not less, dominate the types of stars in our universe. There are 3/4 of these stars make up the stars in our own galaxy. The reason that's important is there's preliminary evidence to suggest around all of these M dwarfs, which you can't see in the night sky, have at least 2 planets orbiting them. So if you think about the fact that there's hundreds of billions of stars in our galaxy, and each one of them has at least 1 planet, and some of them have 2, it just speaks to the huge number of planets that we are certain are out there. Let's go to number 2. Planets with sizes between half, like Mars, and twice the size, maybe a super-Earth, are the most common types of planet. That's important. If you just knew number 1, you might say, okay, that's great. There are a lot of stars, but what happens if they're all gas planets or icy giants? It doesn't bode very well for life, does it? But now we find out that the most common type of planets are those that are sort of like our own Earth. Here's some early statistics from an unpublished candidate list. Down here we show the sizes of the planets, and you can see planets that are about the size of Jupiter or larger are a minority. Even though they were amongst the first, they are a minority of the sizes of planets we're finding. And if you take the Earth size and the super-Earth size, and if you allow me to add them together and refer to them as Earth size for now, you'll see that these two together are the most common types of planets. That bodes extremely well for life. Now, that's all well and good, but what happens if these Earth-sized planets are really close to the star? It'd be really, really hot, wouldn't it? Or if it was very, very far away, it'd be very, very cold. So how many of them are actually in a temperate zone? That's what we really want to know. Well, Kepler has come to the rescue again. Planets with sizes half to 2 times that of Earth orbit in the habitable zone of their stars. What's this habitable zone business? The habitable zone is just simply a region around any star where a planet is just right to have liquid water on its surface. If the planet was too close, it'd be too hot, the water would vaporize. If the planet was too far away, it'd be too cold, it would turn to ice. Water, we believe, is really important in the search for life. Wherever we find water on this planet, we find life. So let me give you a little bit of data here, and I'm going to be very conservative, very conservative. 1 out of every 10 stars similar to our own appears to have one of these Earth-sized planets in its habitable zone. 1 out of every 10. And that's a low estimate. I have esteemed colleagues here in the audience who believe it's actually a few times higher than that. And you remember those M stars we talked about? They seem to be very common around those stars. Early evidence suggests that 50% of M stars have at one planet around the size of the Earth in its habitable zone. That's exactly what we were looking for. I did a back-of-the-envelope calculation. I came up with a minimum of 80 billion planets of Earth size in the habitable zone. That is the type of commonness, the type of numbers we've been looking for. So if there are 80 billion of these guys in a temperate zone, and we're calling them candidate habitable planets because they're about the right size, they're about at the right distance for liquid water, so we call them candidate. But to get to a confirmed habitable planet, which is probably why we're here tonight to find out, we need a little bit more information. We need to know, does the planet have an atmosphere? And are there any signatures of biology? That's what would make it a habitable planet. So folks, we're going to say thank you very much to the scientists and the engineers who worked on the Kepler telescope. They have done a tremendous job in advancing our knowledge. And now we are ready for the next step, the search for life. There are two techniques that we've already been searching for life for the last 50 years or so. The first one we know very well because JPL has been a leader within NASA for all of these decades. The search for life in our own solar system. I love this picture. It's of the Mars Curiosity rover turning around and looking at the crater in which it landed. And I'll have you know that on July 14th, write that down, NASA's New Horizons spacecraft is going to pass by Pluto. It'll take pictures, it'll study it like no other mission ever has. And at that point, NASA will have visited every single large body in our solar system. That's a phenomenal accomplishment in just 50 years. I mean, what are we going to do in the next 50 years? Now, unfortunately, it looks like that the chances of intelligent life in our solar system are quite small at this point. And we've yet to find strong evidence of life. We are not done with Mars. We will continue to look for fossils and other evidence of past life. And we're not giving up on subterranean aquifers where life might exist. And we are certainly remaining excited and hopeful for potential life in the subterranean oceans, the deep, salty oceans of some of the icy moons of Jupiter and Saturn. Here you see Europa. And JPL is playing a leading role in the investigation of this moon. Still no life? Let's go to number 2. Listening and watching for signs of intelligent life with some of our friends from the SETI Institute, the Search for Extraterrestrial Intelligence. They're up in Northern California, who have used for the last 50 years these large single-dish radio antennas. And just recently, they're starting to use these Allen telescope arrays in Northern California. There's a whole bunch of them. Just listening to hear if they can hear any chatter from alien civilizations, from perhaps one planet to another, from a planet to their large spacecrafts, or maybe the leakage of radio communications like we have on our own planet. Even though we're about to go radio quiet, and we expect that alien civilizations might as well. But this search is well worth taking. We won't know unless we try. SETI has recently acquired another technique in their portfolio. They're looking now for high beams of light that pulse at very, very short frequencies. And it's sort of like an optical Morse code, if you will. They've been doing that for about a decade, and they haven't seen anything irregular to date. The search continues. Which takes us now to our next approach. Approach number 3, which is what I'll spend a little bit of time explaining, probing the atmosphere of exoplanets for biological signatures. So what's a biological signature? Basically, as an example, the gases that we release as a byproduct of life that remain in our atmosphere, revealing the presence of life. For example, plants give off oxygen. Oxygen is consumed by humans. We give off carbon dioxide. There are bacteria that give off methane. If we can capture any of these gases, they could be related to life. Let's take a deeper look at that. First of all, I have to remind you that when you see planets in the night sky, so here's Venus, here's Jupiter, that's our moon. You see them not because they're self-illuminous, right? These planets don't glow in the dark. You see them because they are reflecting the light from our sun into our eyeballs. That's how we see the planets. So the same technique for looking for life on exoplanets. So here's a star. It's emitting light, and I've exaggerated the atmosphere of this potential exoplanet. As the light passes through the atmosphere of this exoplanet, it could reflect off a cloud, it could reflect off the surface, and then it makes its way to our telescope. Now, on the way through the atmosphere and then back out again, if it encounters certain gases, like the ones we just described, they absorb light at very specific frequencies. So when we capture the light in our telescope and pass the light through a prism and break out the light from the planet into a rainbow of colors, scientists will then look for the missing light. Right? So in an interesting way, the absence of light in our data reflects the presence of gases in the atmosphere of the planets. And then, thanks to quantum mechanics, we could map the exact frequencies, the exact wavelengths, the exact colors to very specific gases. There is no doubt about the correspondence between the missing light, their wavelengths, and the gases. So this is what the actual data looks like. You're looking at real data. Let's show you how the astronomers interpret this. Because one day you're going to read the New York Times and it will say NASA or an astronomer has discovered life. This is what you're about to see. This series of squiggly lines is what our evidence for life is going to look like. I apologize, no green aliens, no flying saucers. This is what it looks like on exoplanets. So here's a rainbow of colors. I've mapped it perfectly to the wavelengths. You see there's no color out here simply because we've entered the regime of the infrared. The infrared has no color. That's okay, we can still measure it. And on the vertical axis, we have the relative brightness. So for example, up here, we have a lot of purple light. Over here, we have less yellow light. And out here, we have even less infrared light. If the planet had no atmosphere at all, the curve would look something like this. So every single one of these dips corresponds to a gas in the atmosphere of that planet. Let me share with you 3 of them. This thin line is oxygen. This broad line is water. This trough here is methane. So if we saw that, how would we interpret that data? Now, I remind you, this spectrum here comes from our favorite planet, comes from the Earth. So if you were aliens from far away and you got this data, how would you interpret it? Would you be able to conclude there was life on this planet? Well, let's start off with methane. Methane comes, besides leaks in natural gas, it also comes from bacteria. Bacteria in the digestive tracts of ruminants like cows and sheep. So burping, farting cows. But it may not be just that. We have to be very careful in our interpretations. They could also be water reacting with particular types of rocks like olivine. In fact, that's what we think is going on Mars. Some of you may have heard that we've discovered methane on Mars. It very well could be a non-biological source. Water. So this much water, this is what we call a broad line. This much water infers a lot of water vapor in the atmosphere. And if you know your planet is in the habitable zone of its star, now you're thinking, wow, that water vapor may very well be related to liquid water. So now we're feeling pretty confident that we're onto something big. And then oxygen. Oxygen on Earth comes mainly from photosynthesis, from plants and bacteria. So if we find oxygen, that would be a very exciting and momentous occasion, especially because oxygen is so reactive. It loves to rust things, and it loves to solubilize in oceans. So if we find this much oxygen, we know something is continuously generating the oxygen. So that points to possible evidence of life. And it loves to react with hydrocarbons. So if we find methane, in the presence of oxygen, that is practically a slam dunk for the conclusion we have found life. We may not know if it's intelligent life, but we definitely have found life. Now, let me take a step back. We have no clue of what life might look like on another planet. So we have no idea if it will follow this or take a different path. So when we build our future instruments, which we are, we have to make sure that they are sensitive enough and robust enough to measure a whole slew of gases and different types of phenomena, so we can piece that story together and conclude what is it that we have found. Oxygen by itself, water by itself is compelling, but it's the whole story together that allows us to conclude whether or not we have found life. All right, what's special about this technique is we have to capture the light from the star and the planet. It's not like those other techniques that were indirect. We have to capture the light from the planet. So now let's move over to the technology portion of our journey. It's called direct imaging of exoplanets. Very few exoplanets have ever been imaged. Out of those 1,800 planets that we discussed earlier, only maybe 36 or so have actually been imaged. And they all are the same. They're big, gaseous, young, hot, self-illuminous planets that make it easy to take a picture of. No small, older planets. All right, do you remember this chart here where we talked about how the light from the star reflects off the planet into our telescopes? I didn't mention one important thing. The telescope is certainly going to receive the light from the planet with potential evidence of life, but it's also going to receive a lot of light from the star, right? So when a telescope stares at a star, it doesn't see these beautiful planets like I show here. It looks like this, a big, glaringly bright star. In fact, this one was so bright that the light was scattering off some of the support optics, the support structure within the optics, and that's what all this scatter is. So how are we going to find planets through all of that? Right? What we want to do is dim the light of the star so that we can see any potential planets orbiting really close by. That is really hard. How hard? An Earth-sized planet in the habitable zone of a sun-like star is 10 billion times fainter than the star. So let me put that in context for you. You see this little planet over here? It is 5,000 times fainter than the star that we masked out. 5,000 times. So stare at this planet and now think of something that's 10 million times fainter to get to 10 billion. That's the challenge we have in front of us. Oh, and by the way, it's even more complicated. Imagine it's like trying to find a little teeny-weeny firefly that's flying randomly in some direction around an enormously bright beacon of light. And the lighthouse is off the coast of New York, and we remain here in Pasadena. That's how hard this is. Okay, so our challenge is to take a star like this, remove as much of the starlight as possible, and then probe the outer regions for evidence of planets. Let's take a look at the two techniques that are being championed here at JPL. In fact, I see a lot of the engineers that are working on these very challenging technologies. First one, the coronagraph. It's a small optic that fits inside the telescope. Its job is to block the starlight. The second technology is the starshade. Same thing, instead of this little optic blocking starlight inside of your telescope, this one is going to block the starlight outside of your telescope. There are pros and cons for both. Why don't we go ahead and start with the starshade? Now, who better to explain the starshade than our beloved Carl Sagan? This clip was taken from circa 1979. I don't know if any of you have ever seen this.
And on those other worlds, are there beings who wonder as we do?
Here is a light bulb, which is supposed to represent a nearby star.
And next to it, and very hard to see because of the bright light, is a planet. Now we'll need a volunteer who would like to come up, please. Ordinarily, you would have a hard time seeing the planet because it's so close that the star washes out the planet. But if we were able to put something in front of the star to make an artificial eclipse, then we might be able to see the planet. So I'm going to stand over here. Imagine that I'm a telescope somewhere near the Earth, and Tab, if you'd slowly move the disk across, good, a little faster would be nice. Good, now you're just beginning to cover over the star. I really can't see the planet at all. Keep going. Good, now right there, I can't see the star at all, and I see the planet lit by the light of the star. Now, that is a method for looking for planets around nearby stars.
I love her face. The definition of deep infatuation. Okay, so 35 years later, after that video came out that Carl explained his concept, JPL engineers, in collaboration with our colleagues at universities and in industry, have come up with the concept of the starshade. We fly two spacecrafts at the same time. They separate in space. Here's, oops, let's try that again. They fly together in space. They separate. Here is your telescope. Here is your shade. You can see the shade has unfurled its petals. Now it's extending its inner structure out to the size of a baseball diamond. These are two individual spacecrafts. They communicate with each other. The shade is now heading towards its first star of interest. The telescope is aligning itself to it, waiting for the shade to pass in front of the star. And then we see the reflected light from the planets. It's really an amazing technique. Let's take a closer look at this technology. So the star shade itself is tens of meters in diameter. It blocks the starlight. If there happens to be a planet, its light will skirt the edges of the shade and enter the telescope. Once it enters the telescope, it goes through the prism. The prism breaks it out into a rainbow of colors. We look for evidence of life. The distance between these two spacecrafts are 30 to 50,000 kilometers. So to put that in a ballpark that maybe we can understand more readily, 3 to 4 Earth diameters. And then as these two spacecrafts are aligning, they have to maintain an alignment to an offset of about 1 meter in either direction. That's pretty tight. Once the observation of the star has concluded, either the telescope or the star shade will now slew across the sky and look for its next target. They realign, and we start again. Now, some of you are probably asking, what's with the petals, right? Carl did not show those petals. Well, perhaps what Carl didn't have time to explain to his elementary school class is diffraction. We're going to get into physics here. Here's an aerial view of an island off the coast of Norway. You can see the ocean or the sea is moving from the bottom right to the top left. You would think that this island should act like an umbrella. It should just stop the waves, and behind it there should be just still water. And that's absolutely what you don't see behind it. You see the effects of diffraction, the bending of light, the bending of water. You could see it's bending this way, it's bending this way. So back here, there are plenty of waves. Same over here. Land masses don't seem to stop the effects of diffraction. Let's take a look at a simulation by some colleagues at St. Mary's University in Canada. Imagine the star shade is placed edge on, and it's right here. Again, you would think that the star shade would just block all the light. So back here, you would see nothing. Well, sure enough, because of the effects of diffraction, the light has bent around it. So if you're interested in putting a telescope there or a camera, you're going to be still blinded by the light of the star that went around your starshade. So the petals are analytically designed to not stop diffraction. You could never stop diffraction, but you can redirect it. You can redirect it away from your telescope and your camera such that there's a dark shadow behind it. Here's a computer simulation that shows how the petals work. They send all the light to the outside, leaving behind a very deep and dark shadow where we can maybe find the faint evidence of these exoplanets. So here's your shadow, and that's where you place your telescope. The telescope just has to sit in the shadow created by the starshade. You're probably also wondering about now, how do we get something the size of a baseball diamond folded into a rocket? Well, let's work backwards. Here's your fully deployed starshade. It folds like an accordion, or it folds like an umbrella. The inner portions do. And then you're just left with the petals. And the petals will just furl around a hub, and then you can end up with a very tightly stowed configuration that fits nicely on a rocket. Let's take a look at a demo that we just did recently at JPL. So let's pick up the story where the petals are already unfurled. And here are 3 of our ACE engineers and a summer student in the back. And I'm going to run this video for you. We only put 4 petals on, by the way, because we couldn't fit any more petals in the room. This is a half-scale demonstration. So it's certainly not complete, but it's a proof of concept. And I just want to point out there's a bunch of what we call trusses. And the trusses are folded into each other, and you're about to see them expand. And keep your eye on the petals. How do they go from a vertical configuration to a horizontal configuration? I'll give you a hint. There's a couple very small motors in here that are pulling on a steel cable. And as they do that, everything starts to expand. Okay, here we go. We sped this up a little bit. Now, oops, sorry, I did that again. Let's try it again. Okay, here we go. So we've sped this up. This engineer here, by the way, is keeping his eye on the motor. That's one of the 2 motors. And it's like reeling in a fishing line. As the cable gets reeled in, it spreads out these trusses until they continue to elongate. And then at a certain point, in fact, you can see they're still not fully deployed. Wait for it. At some point, they're all going to snap into position. Right there. Just before there's a little hiccup there, and it's fully deployed. The good news is that there's a lot of heritage for this type of technology. We've borrowed from our friends in the aerospace industry that have flown things like this for radio communications and antennas. In fact, there's one right behind you in the corner. That's the SMAP telescope that was just deployed just a few months ago using some very similar technology. So we're confident that it would work. The engineers at JPL have simplified the design, making it simpler, lighter, and integrates with the petals. We encourage you, perhaps during an open house, to come and visit us. We'll be perhaps a little bit more mature than we are today. All right, how about how it works optically? So our colleagues at Northrop Grumman here in Southern California received a grant from NASA to demonstrate how this works optically. So here's Northrop Grumman's setup in a dry lake bed in the deserts of Nevada. Here's your telescope. 2 kilometers away, you see a simulated star. It's a very bright lamp. What you don't see are the simulated planets that are next to the bright lamp. And then in the middle is a prototype of the starshade. And the shape is really, really important. In fact, I brought you a sample. And this is something we've tested or will test in the desert. The actual starshade will be about 120 times bigger than this one. And what you don't see, and maybe afterwards you can come up, these petals have lots of wiggles. And those wiggles are critical because they help with the diffraction of the starlight. Let's take a look at some of their early results. So they're going to move the star shade in position in front of the lamp, and boom, right there, there's our first planet. I'll let that run again. So the objective is to get to see planets as close as possible to the star shade. Okay, so let's take a look at some of their data. They were thrilled to get this bright planet, but do you guys see this faint planet? That was the one they were really excited about. That's getting a little bit closer to what we're looking for. That simulated planet is 100 million times fainter than the simulated star. So we're getting closer to our overall objectives. We acknowledge that the sizes are not exactly what we expect in space. As we mature our demonstrations, they will get a little bit closer to what we will actually fly. But it's a good start. All right, let's now go to the coronagraph. So imagine taking that big star shade and shrinking it down so it can fit in between your fingers, and put that into your telescope. The motivation for the coronagraph comes from studies of the corona. So the corona is these faint, wispy structures in the atmosphere of our sun. And they could only be seen when we have a perfect eclipse of the sun by the moon. Well, if you're a scientist wanting to study this, it's kind of a long time to wait for an eclipse, and then you have to travel to the other parts of the Earth. So a French astronomer asked the question, why not have a synthetic eclipse that he could put into his telescope and observe the corona anytime he wants? That's exactly what he did, and he was very successful in observing the corona. However, as we've just learned, these circular disks are not that effective because of diffraction to look for faint planets. So astronomers here at JPL, as well as elsewhere, have worked over the last 20 years in modifying these masks to take care of the diffraction, to redirect it. Same thing. Let's take a look at how the coronagraph works. This is probably a good time to dim the lights. And you might recognize the narrator, but enjoy this. This exoplanet in the distant solar system appears to have features very similar to our own Earth. It has continents, oceans, and clouds. This star has another planet. This one appears to be a gas giant not unlike Jupiter in our own solar system. As we move further away, the two planets disappear into the glare of their sun. The star now looks like all the other stars in the night sky. How will we ever see these planets? We cannot yet travel there, for the distances to even the closest stars are well beyond humanity's current capability to traverse in our lifetimes. We will have to rely on a space telescope. Housed inside this telescope is a science instrument called a coronagraph that is designed to separate starlight from reflected planet light. As the light makes its way to the coronagraph, we also notice signs of small distortions picked up when the light reflected off the tiniest of imperfections in the telescope's large mirrors. With the coronagraph not yet activated, we see on the monitor what the star looks like through a telescope. No matter how large and perfect the telescope is, it turns what was once a point of light in space into a round disk surrounded by concentric rings, the effect of what is known as diffraction. Somewhere behind the rings of light are the two faint planets. As you're about to see, a coronagraph helps directly image faint planets by doing three things. First, a coronagraph blocks most of the incoming starlight using a mask with a dark central region. The mask is carefully designed to redirect the starlight that it does not block off to the edges of the beam. As we see on the monitor, the inserted mask has already decreased much of the central starlight. Secondly, a coronagraph removes the effects of diffraction. When something that looks like a washer is placed into the light path, it blocks the light in the edges of the beam and the rings disappear. We have now managed to remove almost all of the starlight and are now able to view objects more than 1,000,000 times fainter than the star.
But what happens to the light from a planet? Why doesn't it also get blocked by the mask? Because the telescope is pointing directly at the star, the planet's light comes in at an angle, misses the mask, and passes through the center of the washer. But we are still unable to see the planets. If we look closely at the monitor, when we turn up the image signal by collecting more light, what appears to have been a blank field actually consists of blobs of leftover starlight. This scattered light, due to minute imperfections in the telescope's optics, is still hiding the faint planets. So this takes us to the third and last element of the coronagraph, the removal of these scattered blobs. A special mirror is used with hundreds of tiny pistons behind it that can change its shape so as to correct the distortions in the light beam. As the mirror deforms, the blobs of light, as seen on the monitor, slowly begin disappearing, finally revealing the brighter of the two planets. Afterwards, the fainter planet also comes into view. We can now start to see objects more than 1 billion times fainter than the star. Deep within the glare of their star, we have discovered our two planets. And if the light from these is passed through a prism, we will see the light spread out into rainbows of color. But when looking closely, some colors are missing. They were absorbed by gases in each planet's atmosphere, giving us important clues about their composition. The search for life in the universe has taken a new step forward.
So, a little more complicated than it looks. So I just wanted to bring you up to date on where we are with this technology. So here at JPL, I have the privilege of working with some of the finest optical engineers on the planet. And here you see two vacuum chambers that are meant to resemble the vacuum of space. And inside of these chambers are these fairly large optical tables. And on them you will see a setup that resembles the coronagraph. So we get to test the masks and the electronics and these deformable mirrors. So I just wanted to show you some pictures of the masks. Here's the one that was in the animation. Here's another concept from our friends at Princeton University that appears to work equally as well. And here's a more advanced design that we're looking at from the University of Arizona that has some other special features. Here's what the deformable mirror looks like from a company called Zynetics in Massachusetts. And here's some really early data. This data is probably a couple months old. It shows you that the laser light, which simulates our star, is blocked out. And around it, we have probed down to regions that are less than 100 million. Less than 100 million times fainter than the laser light. So we're heading towards 10 billion, and this is a pretty good start. So we're on our way. Okay, we are in the last section of our journey. Let's talk about what concepts does NASA have, what are they thinking about, what are the possibilities. Here's some of the telescopes that we've already had enormous success with. You're all familiar with the Hubble. You're probably familiar with the Spitzer telescope that has revolutionized our understanding of the infrared world. What's interesting is neither one of both of these two telescopes were not designed specifically to look for exoplanets. However, we've learned just enormous amount of information, even though we didn't design it that way. Of course, the Kepler was designed to look for planets, and it has clearly revolutionized our understanding. What's in the pipeline? Well, just in a couple of years, the TESS mission, the Transiting Exoplanet Survey Satellite, is going to pick up where Kepler left off. TESS will use the transit technique, but instead of where Kepler was looking, which was thousands of light year faraway stars, Kepler will look at the closest stars, looking for the closest planets, giving us a better chance to probe the atmospheres of the planets. Followed by, in 2018, the long-awaited James Webb Space Telescope. Unquestionably, the largest and most complicated telescope that NASA has ever flown. I wanted to show you a prototype of it in the yard at NASA Goddard Space Flight Center in Greenbelt, Maryland. It is unquestionably a behemoth. It is almost 3 times the size of our own Hubble Space Telescope. The mirror is so large that it could not fit onto a rocket. So they broke up the mirror into 1 meter class segments, and some of these segments will actually fold so we can fit it onto a rocket. This telescope will certainly find new planets like Jupiters and Saturns. It wasn't designed to find some of the smallest planets, but it does have an interesting opportunity to discover life or signs of life in a small set of scenarios. Here I show you a planet that has a relatively thick atmosphere, and if James Webb is lucky enough to find a planet that is transiting across the face of a nearby star, and this planet has a reasonably sized atmosphere, then the light that's traveling from the star passes through the atmosphere, absorbed by some of the gases, and then when the detector on the telescope detects it, it'll see some of the missing light. So it, in a finite range of scenarios, can actually find the signatures of life that we've been looking for. One of the telescopes that I am very excited about happens in the middle of the next decade. It's not official just yet. It's currently a study, but it's building up a lot of momentum. I would argue that this telescope, WFIRST, which stands for Wide Field Infrared Survey Telescope, is amongst the most compelling science missions that NASA has ever flown. It carries 2 instruments, and one of them attempts to answer some of the most profound questions in all of astrophysics. What is dark matter? What is dark energy? And on top of that, it uses another technique that we mentioned briefly called gravitational microlensing to indirectly detect planets that are further away from the star compared to some of the other techniques. It will complete our knowledge, our census of exoplanets around stars. And then the instrument that I'm personally very excited about is the first high contrast coronagraph instrument, exactly as we showed earlier. We've never flown a coronagraph that is capable of detecting small planets. It's kind of a technology demonstrator, and we're very excited to see if this technology actually works in space. So that's why you saw those vacuum chambers churning away to advance this technology as quickly as possible. I would be remiss if I just didn't say one comment about new ground-based telescopes. There's going to be a heyday of ground-based telescopes in the next decade. There are at least 3 that I know of that are underway: the 30-meter telescope in Hawaii, the Giant Magellan telescope in Chile, and the European Extremely Large Telescope in Chile. These are the largest telescopes ever built. It's not clear how capable these huge telescopes are in detecting planets. The problem with the Earth is we have this atmosphere that distorts light, despite the fact that they come equipped with the most sophisticated adaptive optics. We're not certain that they will be able to correct the distortions enough to detect exoplanets. I would never bet against a ground-based astronomer. All right, after that, so here's the mission that we believe could be the life finder, right? It will incorporate everything we've discussed tonight, and it will just point at stars and hopefully block out the light and look for all those biological signatures. We don't have a name for it yet, so it's got a placeholder called the New Worlds Telescope. NASA is launching a couple teams next year to study the science capabilities, the architecture, and we're very excited to see what comes out. A couple scenarios that have been thrown out. One is something called the Habitable Exoplanet Imaging Mission. Imagine taking the Hubble Space Telescope and making it even bigger and more powerful, and imagine flying it with either a coronagraph or a starshade. And this telescope would be optimized to look for exoplanets. And for those of us in our community who are feeling frisky and perhaps even more ambitious, there are even more ambitious designs on the table. Imagine a telescope even larger than the James Webb Space Telescope, somewhere between 8 to 12 meters. This would be an amazing feat of engineering. So You'll be all made aware of our progress over the next few years to see which of these telescopes, if any, are selected by a decadal survey committee at the national academies who will make their decision sometime around the end of the decade. All right, we're getting to really far out. I'm not sure where I'm going to be in 2050, but I just thought I would share this with you. Once we find life on exoplanets, we're going to be dying to find out a little bit more, right? What does the surface look like? Are there oceans? Is there nightlife? Is there any evidence of photosynthesis? I meant lights. So here's a concept that came out in the 1990s by a French astronomer, Antoine Labergy. And this was way out there in the 1990s. It is still way out there today. So his concept involved flying an armada, a flotilla of telescopes, anywhere between 1 and 6 meters, flying out in space, imitating a humongous telescope, maybe hundreds of kilometers in size. And these telescopes would capture the light from that planet, and they would reflect that light into what I call the mothership, or perhaps the beam combiner, and it would piece together all of that light and be able to maybe make out oceans, continents, maybe a little bit of vegetation. Apart from this, I could imagine us pointing all our radio telescopes, listening for activities, but this would be probably something along the lines of what we would need to look for features of life on the surface. Whew. Folks, we have come to the end. We have come back to where we started, the only planet in the galaxy that we know of that has life. I'll leave you with one remaining image. In 1990, NASA commanded the Voyager 1 spacecraft, that one right there, to turn around from its trajectory leaving the solar system and take one last picture of the Earth. Can you see it? It's right there. So folks, everyone you've ever known, loved, admired, envied, has lived on that planet. Let's take a greater shot at it. This is what Carl Sagan referred to as the pale blue dot. So imagine if we can acquire a picture like that, knowing from everything we've discussed tonight that there are signs of life on it. Would that be transformational? What would that mean for us? Well, at minimum, I think it would inspire generations of young people to go on to science and engineering. It would perhaps revolutionize our understanding of biology and how life formed on our own planet, maybe stir up some more interest in science and astronomy, maybe some investments in our technology. I'll point out that we are not limited by brain power at NASA. We are limited by money. And perhaps it would establish the next frontier of our ability to know where life is and herald in a new era of interstellar communication and maybe even one day interstellar exploration. Much. So I think we have some time for some questions. If you have any, we've set up a microphone, so please go up there. We have a live stream that's being sent out throughout the planet, so if those folks want to hear you as well. I'll be sticking around afterwards, so if you have any specific questions, I'm happy to take them as well.
I have a question about the star shade. If it's several Earth diameters separated from the telescope, it's going to be really in its own orbit, and you can't really have it in a close orbit around the Earth because That's only one diameter. So I did a little looking online, and I found a brief mention of a halo orbit around maybe the L2 point. And so my question is there a limit on how long the exposures can be? If you're in some orbit like that, is when if the star shade and the telescope keep moving relative to each other because they're in these separated orbits.
Okay, so you're absolutely right that if you're going to have such huge separations, you can't fly the star shade around the Earth. The Earth is too bright, and we couldn't, and it incurs a certain gravitational pull on the star shade. So he's absolutely right. We need to find someplace else really far away from the Earth, and there are points of stability in space that orbit the sun that are very, very stable. And one of them is called the Lagrangian 2-point. And that's exactly what we're thinking. That would be an ideal place. It's not the only place, but it is certainly an ideal place. And then once that alignment is made, then the telescope will keep its shutters open for as long as possible. We are eventually limited by some background noises. If there's dust around the star, we'll be eventually limited by that.
Another thing I found was that the shade has to be kind of edge on to the sun, otherwise there's too much light that gets scattered.
You've clearly
So that
done your
would
homework.
constrain what targets you can look at.
So what we didn't talk about is in the star shade always has to know where the heck is the star, right? The sun, right? We have to know where the sun is, because if it's positioned in such a way that it could blind the telescope, that wouldn't be good. So you're absolutely right. There's a range of angles where the star shade will function, and we always have to be aware of it. We're very concerned about the amount of glint that reflects off the star shade that could blind our telescopes, and that's part of our technology effort. Excellent set of questions.
Thank you.
Hi.
Hi. Regarding Glossy 581G, I want to know if the system was discovered by the Doppler spectroscopes or by radial velocity.
So what is it that you know about this star that makes it so interesting to you, or this planet?
What I know about this star that makes it so interesting is that it has the conditions for being a habitable star. It's not too cold and not too hot. There are other stars. There are other planets that are orbiting the star, like C and D, which reflect the greenhouse reflect. And so it's too hot, or it's murky, and it's too distant from the red star that it's orbiting.
So just, if I can cheat just a little bit, just by the name of the star, it tells me that it was not discovered necessarily by the transit technique, but most likely through the radial velocity technique.
I would think it would be radial velocity, but I wanted to verify that.
Yeah. In fact, if you just go on Google to Wikipedia, it actually gives you pretty good information. Yeah.
Thank you.
You're welcome. All right. I believe we have some questions from the cybersphere. There might be aliens who have emailed us their questions. Oh, thank you. So Tony, who's Tony? Tony asks, how does star size affect planetary systems in terms of the number of possible planets? Wow, that's a great question. How does star size affect planetary systems in terms of the number of possible planets? Well, I think the actual answer is we're not yet sure of how it does. There is some evidence to suggest that small stars tend to have actually more planets, but that might just be a bias of our data, that perhaps those planets tend to be a little bit closer to their star, so we've seen them. We haven't been as sensitive to planets further away. Would you have anything to add to that?
Most stars have about the same number of planets.
So what we think is most stars have roughly the same number of planets. We haven't seen any evidence yet that the star size, the star mass impacts the number of planets, but we will get more data shortly. I'll take your question.
Thank you. I wanted to ask about the approach 3 when you were discussing the,
The search for life?
yeah.
Yeah.
You said that we were looking for the biological elements that we know would produce life, like water, oxygen, and methane.
Right.
How do you take into account that on another planet, maybe the intelligent life or even any kind of life doesn't survive on those types of elements? Maybe they use something
Right.
else. How do you take that into account?
Absolutely. Absolutely. In fact, statistically speaking, it's very unlikely that alien life would have followed the same evolutionary track that ours is. I think that's a fact. Well, it's not, we don't know if it's a fact, but it's certainly a hypothesis. So to answer your question, it's important for us, and we will be arguing this amongst ourselves now for the next several years, how important it is to build our instruments such that they are sufficiently sensitive enough to detect a wide range of gases, right? And it'll just be fascinating to see that if we can piece together a whole new set of gases, what could that possibly mean? And that search will obviously detect gases, but then we have to run that through our computer models and see, well, we know these gases can exist on Earth or maybe not, and how do they play with the others? And it'll be a fascinating cottage industry, if you will. So I hope I've answered your question.
Thank you.
All right, Explorer ISS asks, do different stars have different habitable zones? Okay, that's a great fundamental question. So the habitable zone it's not that special. It's an imaginary region of space, but it's all about how bright is the star. The best analogy that I can give Explorer ISS is imagine you've built a campfire, right? So if you want to stay warm at your campfire, if it's a really big campfire, you probably don't want to stay too close, right? So the analogy is that a big campfire, like a big star, its habitable zone is much further away. A smaller, lighter star, like a small campfire, allows you to come a little bit closer. It's more of a temperate region as you're closer, and that's your new habitable zone. So clearly, the star brightness, the star size, defines where the habitable zone is. I'll take your question.
Quick question. Basically, as technology changes, looking long term, like the next 100, 200 years with things like nanotechnology where we can build better lenses and things, if we can take out all the diffusion of light, basically all the scatter, if we were able to do that with technology, would we be able to directly look at almost like a Google map, if you will, satellite image of the planet, or would there be too much debris in space and dust and various dust clouds and things cluttering that? I was just curious.
Okay, so is your question about our ability to probe the surface of
basically
that
how much light is really coming off in this planet? Is there enough that we could actually just image it if we could take out all the diffusion of light?
Okay, that's a great question. So, so for the typical telescopes that we discussed tonight, except for that crazy last animation we showed, typically our telescopes will stare at a star for a very, very long time. So during that time, the planet is revolving around its own center of axis, and it's also moving. So what we get is kind of a mess, right, of light all combined together. So it prevents us from being able to pick out simple and direct details. Okay. Right? That's why we need to go to that really amazing last simulation where we can build a telescope big enough
to catch enough light quick enough.
Exactly. To acquire the light quick enough so we can collect it while it hasn't rotated very much. So we can pick up photo evidence of chlorophyll, vegetation, right, oceans. So it has to happen very quickly. For it to happen very quickly, you need a big, big telescope. That's why we're really hoping, and astronomers should never hope, but we're really hoping, because we're so interested in life, that we can find a nearby star with a nearby planet, so the telescope wouldn't have to be that large.
Gotcha. Okay. Well, thank you.
Hi.
I can't reach this.
Did your father set you up for this question?
No.
Okay.
I thought of this myself. Thank you very much. when you look through the prism, after you take the light from the star, if whatever I understood, how do you understand which gases represent the gaps in the rainbow sheen?
Right. Okay, great. So again, the question is, we have all of these gaps of light in the rainbow. So how do we know which one is which? So one day when you're a little bit older and smarter than your father, you're going to learn about quantum mechanics. So quantum mechanics is the physics of the very small. And the physics of the very small predicts very precisely at what particular colors light will absorb, like be absorbed, right? So when we see these black gaps in our rainbow, we just have to look at a handbook that tells us, well, at this wavelength, these are the type of gases that possibly were absorbed. And because these black bars, these black gaps are so narrow in wavelength, it makes it very easy to do that. I don't know if that makes sense to you.
That makes sense.
Great. Thanks. Oh boy. Go ahead.
If the Starshield mission is launched, that's an awful lot of maneuvering that's going to have to take place to redirect to look at different targets. What kind of propulsion system is going to be used on that, and what type of operational life can that mission expect to have?
Oh, that's a great question. In fact, I'm going to pass the question. I'm going to ask the gentleman standing behind you, who is a world expert in this field, to come to the microphone and answer that question. Douglas?
I was sitting. So there's different technologies we can use, and conventional propulsion is chemical, like are used on these spacecraft. And that is limited capability because of the energy capacity of the fuel that you can fit into a spacecraft. So what we really want to do for the better missions that last longer is to use solar electric propulsion. So that's using a lot of power to generate ions and accelerate it out in the engine at very low thrust. And so that's a relatively new technology, but like the Dawn mission recently, that was an early technology demonstration of that technique. So it's very low thrust, but it's very efficient. So for a given amount of propellant, you can get a lot of motion out of it.
Thank you, Doug. So we have fuel to rotate the starshade. We have fuel and propulsion to keep it aligned. But when it comes to traversing across the cosmos to the next star, then Doug is right. We're considering the fact that we can't carry that much fuel. So solar electric propulsion might be an ideal solution to that problem. All right, what else do I have here? Oh, okay. All right. I'll play along. What inspired you to get into this field of study? All right, so Carl Sagan, Cosmos, Star Trek, and the Apollo missions, right? And I can't help to think how inspirational NASA can and should continue to be. I think, speaking for my generation and perhaps the generations before me, we were all inspired by what NASA has achieved. And that's why having, I think, a well-funded and an enriched NASA will continue to inspire future generations of scientists and engineers like myself to continue to reach for the stars. And this is the best job a person could ever desire. But you don't have to be a scientist. We need lots of engineers, electrical, mechanical. So there's so much opportunity. And I often joke with my boss that we work here at NASA for our second paycheck. Our first paycheck comes with dollars, but the second paycheck is that intrinsic value of we're doing things like this that are just so inspiring that we can't wait to come to work. Folks, I think we've come to the end of our time. I don't see any more questions, so thank you for joining us.